The ultimate goal of modern biology is to watch the complex, high-speed machinery of life unfold in real time, exactly where it lives, without ever having to cut the organism open. But the body is naturally opaque. Tissues are packed with components that absorb and scatter standard visible light, which means any attempt to look deep into a living subject usually results in a blurry, featureless mess. To bypass this, researchers use near-infrared light, within a specific range called the NARI optical window, between 700 and 1000 nanometers, light can pass through skin and bone much like it's traveling through clear glass. However, physics presents a trade-off. While these longer infrared wavelengths penetrate deeply, they are too large to resolve fine details. Scientists are trapped. You can either see deep into the tissue or you can see clearly, but you cannot do both. Breaking this limitation requires a different approach. We have to send that deep penetrating infrared light in, but find a way to generate sharp, high-resolution signals from the inside out. The solution involves up-conversion nanoparticles, or UCNPs. These are tiny crystals doped with lanthanide ions that can be embedded directly into the target tissue to act as internal light beacons. These particles are engineered to be invisible until we need them. They wait inside the tissue to absorb the deep penetrating 976 nanometer infrared light we shine from the outside. Once they absorb that energy, they perform upconversion. The ions inside the crystal act like a ladder, accumulating multiple low-energy infrared photons and combining them to forge a powerful, shorter wavelength emission, like a bright green or a deep red. Because this light is generated right where the particle sits, the signal doesn't fight its way through tissue on the way in. It starts from the inside, effectively bypassing the scattering that ruins traditional imaging. But generating light internally is only the first step. To actually see past the diffraction limit, we have to look at the unique math of how these particles absorb energy. Standard fluorescent materials follow a linear rule. If you double the laser energy going in, you double the light energy coming out. UCNPs operate on a nonlinear photoresponse. Because they require a specific sequence of multiple photons to trigger an emission, they possess a steep energy threshold. As you can see in this data, the nonlinear emission intensity doesn't just increase, it explodes upward. A laser beam's energy forms a bell curve, most concentrated at the center. The weaker outer edges lack the energy to trigger the nanoparticle. By setting a high threshold, those edges gray out, leaving only the peak active, shrinking into a sharp pinpoint. This measured data proves the effect. Contrast the wide, blurry spread of standard linear fluorescence with this tight, nonlinear emission. The pinpoint is now significantly smaller than the beam that created it. By using this mathematical threshold to shrink the focal point of the light, we found a way to bypass the optical diffraction limit that usually dictates how small we can see. We can now take these shrunken pinpoints and use them to scan an entire sample using patterned grids of laser light, a technique called upconversion nonlinear structured illumination microscopy, or UNSIM. The grid acts like a decoder. As it sweeps across the nanoparticles, the interaction between the shrunken light points and the patterned lines captures high-frequency details of the cell that are normally lost or destroyed by tissue blur. The proof is in these deep tissue scans. At 80 micrometers deep, the 535 nanometer light is scattered into a green haze, but the 800 nanometer light retains its sharp, distinct grid structure, pulling clear information out of the darkness. This allows us to see structures as small as 131 nanometers while looking through nearly 100 micrometers of solid biological tissue. Most importantly, it's fast. Traditional point scanning methods are too slow to catch biological movement, but this wide-field approach achieves 1 Hz video rate imaging. We finally have a tool sharp enough to resolve the smallest parts of a cell and fast enough to keep up in real time. For over a century, researchers have been restricted to studying dead, sliced tissues fixed onto glass slides to see this level of detail. Now we can visually track how biomolecules interact and watch cellular transport systems move exactly as they occur inside a living organism. By mastering the nonlinear physics of light, UCNPs have turned the body's dark depths into an illuminated canvas, finally giving us all a direct, front-row seat to the high-speed transit systems that keep us alive.